All right, so yeah, let's get started. So what I'm presenting is a ZK data marketplace, and what that generally is designing a protocol for enabling permission content viewingship, particularly through the idea of NFTs. So the motivation was looking into developing NFTs where the proof of ownership grants more than just the ability to assert ownership. And so the fundamental question was, what if ownership in effects gives you the ability to view and interact with the content, not just be the one claiming ownership over it? And more generally, just sort of explore what kind of things that ZK can bring to NFTs to bring more interactions and bring more functionality. So it helps just to kind of have a general idea of the protocol concept we designed before going into like the details of how it exactly works. Um, So first, a seller will publish some identifying property of the content that can be proven in a snark. The easiest one that I'll probably be discussing mostly through the protocol, even though it's maybe not that representative because it doesn't give a ton of information about the content, is just the hash of a pre-image. Really easy to prove on a snark, and just sort of gives an understanding of how the protocol would work. So seller publishes that, and that's sort of, again, once the property gives like a buyer an indication of what the content is, but more importantly, it sort of anchors the seller as a commitment. And so the buyer will purchase a token, and they'll send the ETH, and that ETH will be held in the contract. And then the seller will have to submit the snark proof, verifying that they have the property, and encrypt the content with the buyer's public key. And then if that snark is valid, they'll retrieve the ETH, and that ciphertext will be stored on contract for the buyer to be able to recover it. And because it's with the buyer's public key, only they will be able to recover it. So that's sort of our first protocol, that I came up with was having, just for one property, just for a hash, the seller publishes the hash on the contract. They're claiming they have the pre-image for it. The buyer will purchase that token. That ETH will be locked up in the contract. The seller will submit the snark proof, this property proof. The ETH will be redeemed. And we can go through. So again, what this property proof is proving is taking some private data, the buyer's public key, and some property or the hash. And it's checking that the hash of the data is actually what the seller claimed or published on the contract. So again, fortifying their commitment, and then encrypting that data with the buyer public key so that the buyer is able to retrieve it. And then finally, the buyer can retrieve the ciphertext and recover the pre-image. So a couple problems with this is it's really difficult to expand the protocol to other types of content. You have to redeploy a whole different contract with different verifier on contract. And because you're having to encrypt that actual content to send it back to the buyer itself, that proof has to scale with the size of the message. So what we would prefer to have is some integration with IPFS. So you're having off-contract data storage, but you still have the same security reliability, same ability to prove the validity of whatever the seller is trying to sell. And so a really naive way is saying, oh, we could just substitute the content with an IPFS link. But the problem is then the buyer has no way on contract of determining whatever's on the IPFS link is truly what the content you're looking for, or is actually what the seller is claiming is on there. So you have to have sort of a two snark system that I'll go through here, and it's a little bit more complicated, but enables you to host whatever content on IPFS in a permissioned way and still have the proofs on contract. So there's going to be two snarks that I'll be discussing. One's called a property proof, and one's called encryption proof, and I'll explain more of those as we go forward. So similar setup, seller will start by publishing a property snark, but this time on IPFS. And so they'll have to anchor that in the contract by putting this IPFS URI as well as the key hash. So I'll explain a little bit what the property proof is. For the hash example, it's similar, but a little bit different. Again, you're having this private data. This time you're adding an additional private key and the hash or property you're trying to prove. So we'll check that hash is the correct, or that property is valid. And then instead of encrypting the data itself, it's encrypting the data with the key and then outputting the hash of the key. And I can explain a little bit more generally, but once I finish the protocol, it'll come a little bit more clear. but this makes it really easy to substitute in different properties because it's the three same general steps that will enable the protocol to inherit a lot of different properties. So because you're just doing the same general steps, proving a unique property of the data, computing and outputting an encryption of the data, and then computing and outputting a hash of that key, the encryption key. So once again, the seller will register the IPFS URI and key hash on the contract. And this is just so the buyer is now going to have to be able to act as a verifier themselves to verify that this key hash is valid with the IPFS URI. So that's the second step is they'll check that property snark proof that's on IPFS for one is valid. And also that key hash that was output matches what's put on the contract. If they don't have that, then the seller would be able to put something on IPFS and then maybe put an IPFS URI with a completely different key hash. So they could completely debug the whole protocol. And so if that verification succeeds, then the buyer will purchase the token just as before, and the ETH will be locked up in the contract. And then, so this is the second snark proof that they have to use. The seller will submit an encryption snark proof to the contract, which will redeem the ETH. And this one is it's sort of a partition of that original protocol one, where you're separating the proof of the property from the encryption with the buyer public key. And so what is going to be, you're taking in that private key that was originally in that IPFS proof, the key hash that should have been registered on the contract with the IPFS URI, and then the buyer public key. You're checking that they're trying to encrypt the correct key, the one that was already stored on contract and verified by the buyer, and then you're outputting an encryption with the buyer public key. And so now, when in the recovery phase, the buyer can retrieve the key ciphertext from the contract and decrypt that with a private key, and then use that recovered key to decrypt the data ciphertext that was put on IPFS. And so, like I said before, what this makes it really easy to do and why it's a much better version than version 1 is the encryption proof doesn't scale with the content. You're going to have the same key size, so you can keep that constant and you don't have to reapply a contract because that same protocol can be used, and the protocol or the property proofs can be interchanged. Those don't have to be done on contract. They can be done off contract as long as the buyer just knows what they're proving and asserting. And so some things that are still left, and as we've sort of discussed in over the past few weeks, things we would like to maybe get better at is the fact that it's multi-step asynchronous and quite a few steps. The data guarantee, there's no data guarantees because it requires the seller to do its part. So it's a little bit, it almost kind of views ownership as sort of an unguaranteed promise rather than actual ownership of the content. And then after selling the tokens, the seller still has the data. So things that could potentially be added to the protocol later would be fixing some of these issues. But here's a quick demo, because here, the biggest thing here is finding what properties are able to successfully disguise the data in a way, but also give some valuable information to the buyer. And so like I've been using this hash example, which doesn't give the buyer a ton of information, but we're fortunate that we're able to sort of come up with an example using Dark Forest where planet IDs are in fact the hash of the location. So the hash actually does give the buyer some valuable information, where somebody could say, I know I can prove to you I have the location of this planet with this ID, and you can execute the protocol that way where you recover the location. So here's that demo. So the seller is putting in the coordinates of the Dark Forest planet they know. The buyer is going to view it, and they'll go through the verification, purchase the token. They note it's a valid NFT. So then the seller has to then redeem the ETH by generating the proof and encrypting the key for the buyer. And now the buyer can go back and recover it. And so one other demo, this was sort of another just proof of concept that I came up with. It's not really that useful yet, but the idea again is finding things, content where you can prove some mathematical property about them, but also have that property reveal something such the buyer has confidence in what they're actually using or actually what they're getting. And so this example is not this one, is it's an early stab at sort of encrypting an image. Maybe if the idea is you're applying some sort of blur onto the pixels in a way that's decryptable, but because it's only a little bit of a blur, you're able to sort of assert some value to the buyer. And this example is a little bit more contrived because it's the ciphertext that you'll be getting is just an XOR with the key. So obviously what you'll see here is this could be perfectly random, but the general kind of idea is there that you're able to do these kinds of property proofs with the same contract, with the same protocol, by just adding on these different snarks onto IPFS. And so same general idea. Now the buyer will be able to go back and recover the image. Yeah, that's it. So sort of like I've been saying, the big thing now that this protocol is there, and we know we don't, it's kind of, it's pretty abstractable in that you don't have to have these encryption proofs change size with the content, and you can keep adding different property proofs without having to change the fundamental contract itself. You're just adding on to what is an existing system. But yeah, that's all I have.
Nick, I have a question.
Can you hear Nick?
Yep.
Yeah. I was wondering, so this has actually been something that's been on our list with regards for their build. I was wondering if you could walk through how this is used to transact like location data randomly on chain platform.
Wait, sorry. Can you get closer to the laptop?
So basically, this is one thing that's been on our wish list for Dark Forest for a while, in terms of allowing people to transact data privately. How would you use this construction to allow people to on-chain privately transact like location data?
So I mean, so in the demo I was showing, it was like Dark Forest interoperable in that it was checking whatever hash was proven is a valid planet and getting the correct salt for the hash.
Mm-hmm. Oh, gotcha. I think I just missed. I actually stepped out to the bathroom midway. So.
Oh, okay.
I was just making sure. Okay, cool. Thanks.
Yeah.